Hi, and welcome to the last video. You've made it. So in the last 5 video, we've learned all about null and alternative hypothesis, p-value, significance testing, types of errors. And we're going to kind of put all of that together in this last session and talk about how they impact statistical power. So without further ado, let's get into it.
Statistical power. It's the probability of detecting an effect if there is a true effect to detect. And the effect here referred to our null hypothesis that there is no difference between a mean body weight of men ages 25 to 35 between the 1990s and now. So we're saying that both belong to the same distribution. And more intuitively, we can think of power as the probability of rejecting the null hypothesis given that it is false. So if we look at this last part here, and we rewrite it as not rejecting the null hypothesis given it is false, we're really saying that we're accepting the null hypothesis, right? And if we look at back at our charts, our truths and our conclusions from our analysis, this is essentially saying it's a type 2 error. So we can think of power then as the probability of not making a type 2 error. Okay, let's think about an example. Say our calculated power for an experiment we design is 80%. So what does that mean, 80% power? It means that the study has an 80% chance of the test having a significant result. And as power increases, the probability of making type 2 error decreases, right? Remember, we're saying that the probability power is the probability of not making a type 2 error. So therefore, if our power value increases, our type 2 error also decreases. And this will make a lot more sense when we look at our charts later, and I also have a little simulation from a very talented individual later that I'll show you. So if power is one of the components that influences the conclusion you might reach from a statistical test, are there others? Yes, there's actually 3 others, 4 if we include power. And the first one being sample size, and that's just the number of observations in the study. We can visualize this later, but essentially increasing the sample size will result in a higher statistical power because we're just decreasing that standard error. And then there's what's called an effect size, which measures the magnitude of the experimental effects. And the effect size we want to detect is kind of the minimum size of the effect that you hope to be able to detect in a statistical test. And then there's the alpha level, which we already talked about. It's the significance level, right? It's from type 1 error, and it's the odds that the observed result is due to chance. And we can conceptualize this as the type 1 error, as we've discussed before. And lastly, power is the odds that you will observe a treatment effect when it occurs. And you can imagine that if we specify any 3 components, the 4th can be calculated. So let's actually conceptualize what drives power. We can do that by drawing 2 sampling distribution that we should be very familiar with by now. And so these are just made up sampling distribution for some data we collected. So the first thing we need to look at our statistical distribution is, let's say that our distribution looks like this for both our sampling population, where there are some overlap between the 2 distributions. We can have then a scenario where the null hypothesis is true and a scenario where the null hypothesis is false. Say that our population mean under the null hypothesis is some value of mu1 for our left distribution here, which will be the center, and then for mu2 it's also in the center for our second sampling population that we collected. Then we need to set a significance level, or alpha. This means that if we take a sample from our population, we calculated some statistics mean, and it just happened to land in this red shaded alpha region here, we are rejecting the null hypothesis and then giving a scenario where the null hypothesis is actually true and we don't know that, we will be committing a type 1 error. For power, where the probability rejecting our null hypothesis, let's look at the sampling distribution for that, for our mu2 on the right side here, right? And in this example, we should not be rejecting the null hypothesis, assuming it's false. But will there be samples in which will cause us to not reject the null hypothesis? Yes, right? If we sample and we land in this shaded blue region here, we're going to be committing a type 2 error, where in this example, we should not be rejecting the null hypothesis, assuming it's false, but there will be sample that will land in this area where we will not reject our null hypothesis, even though it is false, and thus we're making a type 2 error. So essentially, this is the probability of making a type 2 error when we should reject our null hypothesis is in this area. So if we just so happen to sample it. And then our power, the actual probability of rejecting our null hypothesis, given that it's false, is in the rest of the shaded area. And say we collected some measurements, perform our statistics, and our sample statistics just happen to land in this area, we would correctly reject the null hypothesis that our data came from the same distribution. However, if we were to repeat this experiment and we just again happen to sample our statistics and end up in this shaded blue region, then we would not reject the null hypothesis. Therefore, the higher the power, the higher the chance or the probability of us not making this type 2 error. Thus also brings up the usefulness for having a good number of replicates, right? Now let's think about how we can actually increase our power. So if you remember that those components, increasing alpha is actually one of it. If we look at alpha or the significance level here, we can increase it. By increasing it, we can also increase our power. But in doing so, I hope you can see this, you're giving yourself a higher chance of making a type 1 error because now this shaded region is even bigger, right? But our chance of making a type 2 error is smaller. So this makes sense, right? Our alpha level is 0.05, and if we increase it, we will reduce the chance of making a type 2 error, but we're also increasing our chance of landing in this type 1 error region in the scenario that our null hypothesis is true and we just don't know it. And another way to increase our power is actually increasing our sample size. Increasing our sample size will make our distribution even more narrow, and it decreases the probability that we will not reject our null hypothesis by reducing that area. Other things that could affect our power is the deviations or the variance, which will directly affect how, also directly affect how narrow our distribution is. And the other thing is the effect size, which we talked about briefly when we list out those 3 components, power being the 4th. So the effect size will affect how far apart our distribution is. Because effect size can only be calculated after we collect our data, we have to estimate it for a power analysis. The common practice is to use a value of 0.05 as it indicates a moderate to large difference. So in summary, for calculating power, you need to specify sample size, effect size, and significance level. Most commonly though, you want to calculate the sample size needed given a specified power, effect size, and alpha. What power and alpha value you specify is up to the experimentalist, what he or she is comfortable with, and what kind of trade-off is appropriate. Alright, now that we've talked about statistical power, we can play around with some parameters and get an even better understanding. So this website simulates the parameters of power, and you can solve for certain things like power, alpha, sample size, and even the effect size, co and D's here, if you specify the other 3. And the link for this will be in this description. So let's solve for power first, and let's look at our parameters under here. We have the type 1 error. We have at the given setting, we have a 10% chance of making a type 1 error, 12% chance of making a type 2 error, and our power is quite high, 88%, given a 20 sample size. Let's increase that sample size. And you've noticed, keep focus on a type 2 error and type 1 error here as we increase the sample size. Say we increase it to 30. We're decreasing our type 2 error, but not changing the type 1 error. Thus, it's yielding us a higher power in general by just increasing the power size. And remember, by increasing it, we're making our curve narrower and the overlaps are even more narrow, right? And this beta 2 here, you should understand from our lecture, is the type 2 error curve. If we decrease sample size, it gets bigger. Thus, we're more likely to make a type 2 error. And if we increase it, that decreases the curve because the sampling distribution are now much narrower and they don't overlap as much. All right, another thing we can do is, like we talked about, significance level. Let me just set this back to 20 to reset things. All right, let's look at how we can increase our power by increasing the significance level. So pay attention to the power here and pay attention to the type 1 error here, right? Let's say we increase it to 0.15. We're increasing our power, but also increasing our chance of making a type 1 error. And that's because we're increasing the shaded region here, and it's decreasing our chance of making this type 2 error. But the trade-off is that we're also increasing our probability of making a type 1 error. Lastly, if we already have done the experiment and we know the effect size, we calculate the effect size, and let's say that the effect size is actually 0.75. That actually will yield a higher power as well, but not changing the type 1 error at all. Realistically, though, like we mentioned, usually experimenters want to determine how many samples they should run for a given experiment. And then to do that, let's say we want to calculate the number of sample size, and we have to specify a power, right? We want at least a 0.8 power, 80% chance. And let's set this back to 0.05, and the effect size, let's 0.5, right? So in this experiment, you need at least a 30 sample size to have an adequate amount of power, 80% or higher, right? You still have a 20% chance to make a type 2 error, but you have a much higher chance of landing in the shaded region where you can reject your null hypothesis, assuming it's false.
Congratulations on finishing the course. You've watched all 6 videos, and hopefully they have given you a great understanding into statistical power, as well as some of the basic concepts of statistics that you might have forgotten from your days in college. Thank you, and we really hope you enjoyed this. Please, if you like it, leave us a comment, share it, and email us with some feedback, even suggestions, future videos that you want us to do explaining other concepts. Thank you.